In the previous lesson, we discussed about energy, and we define energy as the capacity of an object or something to do work, right? So if you have no energy, if you have not had your breakfast, oh yeah, I can't do any work, yeah. But what do we mean by work, right? Typically, in the layman term, work generally refers to your job, right, or your homework as a student. But in physics, work means a very different thing. It is due to a force exerted by an object or a being, right? So how do we actually calculate work done, and what exactly does it really mean? We discuss this in this video today. So let's get right into it. Hey guys, what's up? Welcome back to the classroom. It's Mr. Low, and today we are going to go through the next section of the topic, or rather the chapter of work, energy, and power. So in the last video, we discussed about energy. We talked about kinetic energy, gravitational potential energy, as well as the very important principle of conservation of energy, right? Which states that energy cannot be created or destroyed, but it can be converted from one form to another, right? But now we're going to move on to the next concept that we need to know, that's called work, or rather work done. All right. So in this lesson, we are going to define what work done is, okay, by a force. And we're going to recall the formula work done equals to force times distance and apply it to solve some problems. All right, so let's carry on. Okay, so just now as I was saying, when we talk about work, we don't really mean the homework or the job that you're doing in physics. Okay, what it means by work done is this. If you look at the definition, which is something that you should memorize, all right. Okay, work done by a constant force here is due to a force, okay, on an object is the product of force and distance. So what is product again? Product means multiply. Okay, so please take down the notes here. It means multiply, right? Okay, so it's a product. So rather you multiply the force and the distance moved by the object in the direction of the force. So actually it means that, okay, if I have an object here and then you apply a particular force F, right, and as a result, this object travels a distance d over here, d here, then the work done due to this particular force here is given by work done equals to force times distance. Alright, now this distance, notice I put two strokes here besides, in front of the distance, the d here. Okay, why do I need to do that? Okay, because this symbol here, represents parallel. Alright, so it represents parallel. That means the distance traveled in this case must be parallel to the force, in the direction of the force, which is actually stated in the definition itself, right? So if you recall that there is another formula that is very similar to this, right, in the previous topic, chapter 5, moments itself. Okay, so let's recall again. Moment equals to force times, it's yet another force times distance. But remember, in the formula for moment, I force, or rather I make everyone write the perpendicular sign. Force times perpendicular distance, right? So let's look at the diagram again. If I have a force over here, force F acting on a plank, all right, then the moment due to this force is force times perpendicular distance. Right, the right angle is over here. So this is why I forced you to write the perpendicular sign over here, because in this topic, this distance here is the distance in the direction, or rather in the same direction as the force. Alright, so it's parallel and it's not perpendicular. Okay, so this is something that you should take note of. Please do not be confused. Okay, moving on. So work done has units of joules. Okay, now if you're sharp enough over here, you realize that this unit, isn't this the unit for energy as well, right? If you recall, let's scroll back up a bit. Okay, in the previous lesson, you can see that, for example, kinetic energy is given in terms of joules. in the units of joules rather, gravitational potential energy is also in joules. In fact, any energy has the units of joules. And you see over here in this in work done, okay, the units is joules. Alright. So this gives you a hint that work and energy, they're kind of related to each other. Okay, so this is actually why we place them in the same topic. Okay, there is a principle that says that work done and energy are really similar stuff. Okay, we'll get right into that later on. Okay, so just to emphasize here, this parallel distance is the distance moved in the direction of the force. Okay, so remember every quantity here has to be worked in as a unit. Okay, moving on. Okay, so this parallel thing in parallel distance tell us that, okay, if the force is horizontal, then the distance moved has to be horizontal. Okay, get the idea? Okay, if it's vertical, of course, if it's vertical, then we are only interested in the vertical distance moved by the object. So at this point in time, let me just do a quick demonstration on what it means by parallel distance. Okay, so let's say I have an object here and I put it on my palm. Okay, you know that this object has a weight which is pointing downwards, right? Something like this. So in order to lift it up here like this, my palm has to be exerting a force upwards in this direction, yeah? So if I were to push this object upwards, right, you can see that there is a distance traveled in the direction of the force exerted by my palm, right? In this case, there is work done. However, if let's say I'm holding on to the thing like this, same thing, force pointing upwards, but I'm moving it horizontally. Can you see that? The distance traveled is in this direction, right? In this direction to my right, but the force exerted is upwards. So in this case, there is absolutely no work done, right? On the other hand, if I'm just holding on to the object like this, okay, there is a force exerted upwards, but there is no distance traveled in the direction of the force, so there is no work done over here, right? So it's summarized over here, there's no work done if, let's say, there is no movement of the object, right? Clearly. So if I'm just holding on to this object right here, just holding on to it, I'm not moving it, there is no work done. Alright, there's a force but no distance traveled in the direction of the force. So that's case number one. Case number two is there's no work done when the force and the distance moved are not in the same direction. Okay, they are perpendicular. So it's very clear in this example here, right? The guy is pushing, is exerting a force upwards to hold the parcel, but he's moving in this direction, perpendicular to the force, the direction of the force, right? So in this case, there's no work done. All right, so please bear that in mind, right? Then we can go ahead and calculate, the work done due to a particular force, right? So calculate the work done in each of these cases. This one is very simple. Okay, work done is force times perpendicular distance. Remember to quote the formula. I keep emphasizing that. Yeah. Okay. Force 20 newtons. Distance in the direction of force. Remember, it must be in the direction of force. 4.0 meters. Right. So you just multiply it and you get 80 joules. Right. Here is an example where it gets a little complicated. Okay. This object here is being pushed up a slope. Right. So you can see that there's this slope here is like a right angle triangle, right? 3 meters by 4 meters by 5 meters, Pythagoras theorem. Now, the force is 20 newtons, right? And it pushes the box all the way up to the top of the slope here, right? So, we know that the force is 20 newtons, but which distance are we going to use, right, to calculate the work done? So this is when you need to recall very clearly that the work done is the distance that we should use is the distance in the direction of the force, in the same direction. So we're actually looking at 5 meters. Okay, so we're just gonna ignore 3 and 4. These are just distractors. Okay, so we choose 5 meters here to be the so-called parallel distance. Okay, so work done equals to force times distance. You get the work done. Very simply. Please don't be tricked. Okay, so let's come to this example here. Okay, all right, let's read the question together. Okay, a container has a mass of 10 kg. take G as 10 newtons. So this is on Earth, right? Okay, what is the minimum force needed to lift the container? Now, it is always good when we deal with forces, questions regarding forces, to actually draw a diagram. So here I'm going to just quickly sketch a diagram here. Okay, this is the container. It has a mass of 10 kilograms. Now, my job, or rather, whatever, what's the minimum, the jobs of the force is to lift the container, right? So I have this unknown force here. Now, this force is supposed to overcome the weight of the object, right? The object here, there is a gravitational pull from the CG, okay, of the object down, in the downward direction. That is the weight, okay? So the weight here. Now, in order to lift this box up, you don't need to know physics. Anyone can tell you that you need to exert a force equal or larger than the weight itself in order to lift the thing up, okay? So this minimum force should be exactly equals to the weight of the object, very simply, okay? So let's go ahead and calculate the weight of the object. First, for part A, recall the formula W equals to mg, mass times gravitational field strength, which is 10 in this case, right? So we can carry on to fill in to substitute in the numbers. Mass is 10 kg, okay, and then we multiply it by 10. Right? That gives us 100 newtons. So in this case, the minimum force required, hence, the minimum force required is simply 100 newtons, which is equal to the weight. Yeah. Okay, of course, you can always exert a force bigger than the weight itself, no problem. But we're asking for minimum, right? Now let's look at part B here. Using the minimum force calculated in part A, that means you must use back the same answer. Okay, minimum force calculated in part A, calculate the work done by that same force in lifting the container to a height of 2 meters, right? So this force here, minimum force, is going to lift the object up, push the object up by 2 meters. So we're asking for the work done, right? So in this case, I think it's very straightforward. Let's just write down the formula first. Work done equals to force times. Okay, don't forget the parallel, right? Just avoid confusion with the formula for moments. Yeah. Okay. Force times parallel distance. Okay, we can go ahead and substitute in the numbers, and that equals to the force in the previous case is 100 newtons, right? Okay, and the distance moved in the direction of the force, 2 meters. Very, very clear, very simple, right? Times 2 meters, right? So, answer, without a calculator, very simply, 200 joules, right? So remember the SI unit for work done is the same as the SI unit for energy, which is joules. Okay, and why is that? So in this example, okay, in this question, part C, you see it very clearly. Why is it that they carry the same units, right? So let's move to part C very quickly. Okay, in part C, I think let me do the working over here. Okay, in part C. Oh my gosh. Okay, sorry. Alright, in part C. Can we just get rid of this already? Okay, great. Alright, in part C, okay, the question asks, what is the gain in gravitational potential energy of the container? Okay, so again, let's draw a diagram again, right? So you had the box, you had the box that was planted or rather placed on the floor, right? And it was moved up by a distance of 2 meters, so it ends up here, right? So the mass of it is 10 kilograms. 10 kilograms. Alright, so we are asked to find the gain in GPE. At first, there was no GPE because it's on the floor, right? And now it is at 2 meters above the ground. So again, let's put down the formula. GP equals to mgh. Okay, if you cannot remember, please go back and view the previous part of this 3-part lecture series. Okay, so GP equals to mgh. Let's put in the numbers. M is 10, and G is also 10, and H in this case is 2 meters. Alright, and you see that the answer here is 200 joules. Again, it's energy, so unit in joules, right? part of the question. So you have calculated the potential energy, the dP of the container. How does your answer, how does your answer compare to that of part C? Okay, so let's look at, not part C, sorry, it should be part B. Typo, my bad. Alright, so please change, no, not B, part B. Please change, right, to the previous part, right? So if you're quick, we will have definitely realized very quickly that these two answers are the same. Okay, now these two answers are the same, so let's write it down. The answers are equal. Okay, so what does this mean, right? This actually tells us something very interesting. The work done by the force, alright, somehow becomes the gravitational potential energy of the object. Okay, so let me just jump back here to my camera view just to do a quick demonstration again, right? So the same object, right? So let's say my palm here is representing the ground, right? The ground. Now I'm gonna exert a force to lift it upwards, to pull it upwards, yeah, away from the ground. So you see there is the work done pointing upwards due to my right hand, okay, and there's the distance traveled in the direction of the force, which is upwards. Now, after I do that, you can see that this object here is off the ground, represented by my palm, right? And it now has gravitational potential energy, right? So what happens here is, by doing work on the object, by doing work, force times parallel distance, okay, I'm actually imparting or putting in gravitational potential energy into this object, right? So my work done somehow has become energy, right? Now let me show you another example here. Okay, if I have a flat surface like this, I'm going to use the TYS to represent the floor. Okay, if I have a flat surface like this and I'm just pushing this object, I'm just pushing the object like this. Okay, so there is work done because there is a force exerted and there is a direction traveled in the direction of the force. Right, now what does this object now, what energy does this object have now? Answer, kinetic energy, right? Because it's moving, right? So by doing work done, I'm actually imparting kinetic energy into the object. So now no work done, no kinetic energy, right? So I hope that is clear for you. All right. Okay, so yeah, so this is what we mean. Okay, in this example, you can tell that the work done by a force becomes the energy gained. Work done by a force on the object becomes the energy gained by the object. Okay, so if you're putting in energy into the object, this is actually called work energy theorem, right? So hope you can see why is it that both this work done and energy carry the same SI units. Alright, so let's do a quick summary here. In this part of the chapter, we learned about what it means by work done. Work done is due to a force, right? It is simply the product, right, of force and the distance traveled in the direction of the force. Force times parallel distance. You can actually see that the definition and formula, they are really related to each other. So this is why I really encourage you all to go and memorize the definition, because in case you forget the formula in exam, you panic. Okay, this is when the definition may help you a little bit. Okay, so work done, because as we saw just now, work done and energy, they're really related to each other. They carry the same units, joules. Okay, and then we done a few examples. So in this particular case, you must know how to identify which distance to take when calculating the work done. All right. And then we looked at lifting, in the case of lifting an object, right, by a force, and we see that from this example very clearly, the work done due to the force later becomes the GPE of the object as the force lifts it up. Okay, so this is work energy theorem. All right, so you can see that how the concept of work done is related to the previous concept of energy, kinetic energy or gravitational potential energy. Alright, so that's it for this video. In the next lesson, we are going to look at power. Right, so I hope you had fun and learned a bit of stuff. Thank you very much for watching. I'll see you in the next lecture. Take care.